Hey, welcome back to part 4 of your 4-bit kinematics series. In this video, I am going to be talking about going over one example, reinforcing the 6 steps of problem solving, which I will apply to this example. You are welcome to skip this video, or you are welcome to check back on at the very end of the video for the solutions after you've seen all the problems. So number one thing before we move on is for question B, I just changed the value here to 0.5 seconds instead of 1.1 seconds. Other than that, let's get right into solving this problem. Like so. We have Hanji from Attack on Titan again. She kicks a soccer ball up a hill with a velocity of 6.6 meters per second. So this is talking about the very beginning where the ball starts to roll up the hill, and which means this is our initial velocity of our soccer ball. So our soccer ball is the object that is moving in this case. It's rolling up the hill. It stops after 2.95 meters. The units tell us is a displacement. So that's the displacement for our problem. This also tells us one other thing. As it rolls up the hill, eventually a ball stops, right? And once it stops, we know that at that point, our velocity is 0. The question A is asking for the acceleration. First things first, we are going to draw a picture. So I'm going to draw a picture on the side here. We have a ball that's being kicked. At the very beginning, it starts off rolling very fast, and as it goes up the hill, it slows down and finally to a stop. I'm going to label my positive direction going up the hill. Okay, now I have a picture. We are going to write down what we know and what we don't know. We do know the initial velocity here is 6.6 meters per second. We know the final velocity here is 0 meters per second. We know that the total displacement of the ball up the hill is 2.95 meters. And what we need to find is the acceleration. I'm going to write down the 4-bit kinematics equations on the side for our use in this entire problem. Since we're talking about acceleration, we know we have to use one of these 4-bit kinematics equations. Which one? Well, we have initial velocity, we have displacement, we have final, we need to find acceleration. Let's find an equation here that has all 4 of these variables. So if we go down the list, boom, 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 we come up to the 4th one, final velocity, initial, acceleration, and displacement, including the R unknown is in there as well. So let's write this one down, and since we're solving for the acceleration, we need to do some rearranging to give us our unknown. Now, before we do that, we know this final velocity is 0. We can just cancel that one out. We don't have to deal with it when we are rearranging for the acceleration. I'm going to move U to the other side. Because we are trying to isolate for acceleration, we're peeling off the orange, the outside of the orange peel before we can peel the inside, which includes the coefficients of the acceleration. That's 2 and S. So dividing at both sides of the equation cancels that out. So then we get minus U squared over 2S equals to acceleration. Next step is to substitute everything in, which I will do for U and S. Punching into our calculator, we get negative 7.383 with more digits in the end, which I will save in case we might need it later on in another problem. And I'm going to round this up to negative 7.4 meters per second squared, just to match the number of sig figs in the problem. We can check for a few things. First of all, we know the direction is negative. Does that make sense? Well, if an object is moving up the hill, my soccer ball, and it is decelerating, my acceleration goes against the motion, which should be in a negative direction. That negative sign has meaning. It definitely belongs there, so that's a good check. The units I have meters per second squared, so it looks like that, meters squared over second squared, and I divide by another meters, which is going to be on the bottom. One of the meters cancels out, I get meters per second squared, so the units is a check. As for the value, it's hard to say. It's very, especially when we start out with physics, our numbers we're not very sure. But I definitely don't expect this number to be in the thousands and the hundreds or something larger than that. So 7.4 is looks reasonable to me. Question B. Now, we might be dealing with a different scenario, but let's read. After 0.5 seconds, okay. So what does that mean? Does it mean the ball doesn't reach the top of the hill, or does it reach the top of the hill? Regardless, this is telling us the time because it's in seconds. The question is asking us for how far up the hill did the ball roll. Okay, so it means that we don't know whether or not it's reached the peak or not, but we do know this is asking for the displacement. Let's draw a picture. Soccer ball's being kicked, and it goes up, 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 up. It ends up being somewhere, and we don't know whether the ball has come down already or hasn't reached the top yet. We don't know. I am going to write that going up the hill is the positive direction. So let's do some labeling first. Initial velocity here is 6.6 meters per second. We know that. It's traveled for a total of 0.5 seconds. We are trying to find the total displacement up the hill, and now we're kind of stuck. But let's think about this a little bit more. The soccer ball is going up the same hill. It will constantly decelerate. Because the soccer ball is going up the same hill, it will decelerate at the same rate it did before. That tells us that the acceleration value is the same as what we've calculated before. And I'm going to write the non-rounded value in case we need to use it. Actually, we will use it. I've also saved it on my calculator so I can use it again. I'm going to write a note because we are using the same hill. Ball's going up same hill. The rate at which it loses velocity is the same. Now we have all our values. We have our four used variables. Now we can try to identify which equation we need to use. Notice that it's oftentimes 4 variables in every single case we've dealt with right now, and it's probably going to remain the same for that matter. We have S, T, A, and initial velocity. If we zoom in, if we go through all the equations, the one fulfilling all of our needs is this one. We have S, initial velocity, time, acceleration. Let's use that one. And hey, we are finding the displacement. We don't even need to rearrange the equation. So let's write it down and solve. Notice when I put the values in, I used the negative. Make sure I put in the negative sign for the acceleration because it is decelerating, slowing down as it's going up the hill. Let's put all of this in our calculator. This gives us a value of 2.377, I believe. And keeps going, and it's in meters. I'm going to round this one to 2.4 meters going up the hill based on our directions. Doing a quick check whether this makes sense. Our direction makes sense. We got a positive number, meaning that the ball has been displaced positively up the hill. I kind of expect that because that's not a lot of time for the ball to go up and all the way back down again. So I don't think the displacement is negative per se. As for the units, we can double check. We have meters per seconds times seconds, which just cancels out to give us meters. And for the second one, we have meters per second squared for acceleration times seconds squared. Units cancel out, leaving us with meters as well. So units check off. So 2.4 meters is roughly about 2 to 3 strides, depending on how tall you are. So it kind of makes sense, the value itself. Next question, how long did it take the ball to roll up the hill? Let's label our problem. When it's asking for how long, this is asking for a time. And this question is a little ambiguous. I'm very sorry about that, but this is It's looking for when the ball reaches the top, reaches its peak. Let's use a picture to illustrate what that means. So that's just like problem A, where the ball reaches the peak and there's a one point in time where it stops at the very top before it rolls back down again, which doesn't happen in the case because it's just reaching the peak. Going up the hill is going to be my positive direction, and let's label some knowns that we have. We already know from our previous problems, the question, initial velocity is 6.6 meters per second. We know that it stops momentarily at the top, meaning our final velocity is 0. We also know that the displacement is 2.95, as mentioned in the question A. And now we want to find the time. So let's identify what we have and we don't have. We've identified what we have and don't have, and we want to identify which toolbox we want to use. U, T, S, and V. And if we screen for our equations, this is the one that we need. S, V, U, and T. We are solving for T, meaning that we have to rearrange this equation to give us T. We also know that the final velocity is 0, so I'm going to, from the get-go, get rid of that term. Let's start off with multiplying both sides of the equation by 2, giving us 2s is equal to, now v is gone, we're left with ut. So we're solving for the time, so let's isolate the t by dividing both sides by u. That leaves us with time is equal to 2s divided by u. Next step is to isolate for everything. Sorry, next step is to substitute everything in. That gives us a time of 0.8939 seconds. And I'm going to round that to 2 sig figs, so 0.89 seconds overall. Save that on my calculator. So since we're talking about time, no directions are necessary, but if you do get a negative value for your time at any time, that means you need to go back and check your solutions, okay? But we don't expect time to ever be negative. If you do get a negative value for your time, that's a red flag. The units do make sense because we're taking meters and dividing it by meters per seconds. The meters divides out, and because you're dividing and dividing again, the seconds come on top. Another way you can think about it is you can write meters divided by meters per seconds, and every time you're dividing by a fraction is the same as multiplying by the reciprocal. So meters on the bottom and on the top cancel, therefore leaving with seconds. Units check off. As for the time, it makes sense because the ball didn't go very far. It only went up 2.4 meters going up here, which is not all the way at the top, taking about 0.5 seconds. Now, if it reaches the top, it must take a longer time, and 0.89 seconds is larger than 0.5 seconds, so our value does check off. So in relation to the rest of the problem, our answer makes sense in that regards. Everything is consistent. Next problem. After the ball reaches the top of the hill, it rolls back down. Okay, so it's back down now. When it is rolling down the hill, it's going down at 3.3 meters per second. Now, given that our directionality is going up the hill being positive, that velocity there is going to have a negative value. I'm going to label that velocity as our final value because it looks like that's the end point we're looking at, because we know the starting point. We here have a little hint, which I should have put it earlier. The ball, because the slope of the hill is constant for the ball's journey, meaning that the slope doesn't change, the ball would experience the same acceleration for the journey. So the acceleration same as before, negative 7.383 meters per second squared. Now we want, and the question is asking for the total time the ball was rolling since it was kicked. So the kicking is the initial point in time. So this is the beginning, if we do need the initial velocity here. Okay, the ball starts off, it is kicked, goes to the top, and it comes back down. So the ball has actually gone a lot of distance, but the displacement is only there to there. Luckily, we're not asked for displacement, but just to put everything into perspective. I'm also going to label the direction up the hill being positive to give us a reference point for our directionality. We know the initial velocity when it's kicked is 6.6 meters per second. The final velocity here, and assuming going up and back down, is, since it's going down at this point, it is negative 3.3 meters per second. We know the velocity, we know the acceleration because it's on the same hill of negative 7.383 meters per second squared. Let's identify which equation we need. So we are asked for the time, for I got to write that down. So UVAT, let's search it up. With looks like the first one is our hit. V, we have U, we have A, we want to find the T. And hey, we have now used, we'll be using all 4 of our kinematics equations. So let's write it down. Since we're solving for time, we need the time, I'm going to need to rearrange some of these values. Meaning we're going to, again, solve for T by peeling our orange, getting rid of all the terms that are outside of our term of interest, before peeling the inside of our orange by dividing both sides by our coefficient beside the T, so dividing by A. Don't forget to divide the whole side of the equation. We get T is equal to V minus U over A. Time to substitute our values in. Now this is when directions matter. This is a very good example of where someone like me back in the old days may have screwed up if I didn't pay attention to positives and negatives for direction. So final velocity, for example, is negative 3.3 meters per second minus initial velocity 6.6 meters per second divided by the acceleration, which is also negative 7.383 continuous, I will find it on my calculator, meters per second squared. Now, if I did not use the correct directions for final velocity, I would have had a positive number subtracting a negative number. My whole answer would have been completely different. That's why you have to be very careful. This will be very important when we deal with free fall, when things are up in the air and gravity is affecting the motion. Calculating everything, we get 1.34, which we will round up to 1.3 seconds. Checking our positives and negatives, it's a positive value, meaning we didn't do anything silly, because time should never be negative. Seconds, our units, let's double check our units. We have meters per seconds minus meters per seconds, which is just meters per seconds, divided by meters per second squared. If it's easier for you, you can visualize it like this. When you're dividing a fraction is the same as multiplying by the reciprocal. So meters here cancel, one of the seconds cancel out, and we're left with just seconds. As for the value of 1.3 seconds, we expect this value to be larger than the 0.89 seconds because the ball has reached the top and rolled back down already, meaning the time is longer, and yes, it is. So that's our check for this problem. Here we go. This is the example, and we've touched on every single kinematics equation. If there was one thing or two things I want you to take away from this video, number one, I really encourage you to visualize what is happening. What is the motion of your object? The ball going up the hill, then down a hill, and what's happening in every moment. Think of a ball actually moving up a hill. Now, you can't do this on a quiz or test, but if you're at home, make a hill, roll a ball up the hill just to see what happens. It will help you identify some things you may not know, such as the ball momentarily stopping at the top. The second thing I want you to take away is directions. Making sure you put in the correct sign for your vectors. We just learned and saw example of if you did not put in the correct sign, you get a completely different number in your problem, in your solution. So hopefully you found this video useful. and maybe you've learned a thing or two. Please practice more. Otherwise, I will see you back for the next part on Freefall, Part 5.